Before we get into the actual stereochemistry, I want to go over kind of like priorities, right? Priorities that will help you out when you're doing stereochemistry. So the first thing that you should be looking out for is atomic number. So atomic number is going to be the highest priority. What I mean by atomic number is that, let's say you have fluorine, which is number 9, and I have something like, let's say, iodine, right? Let's say iodine. So which one am I going to consider first when I'm counting? Well, I'm not going to count fluorine to be first, right? Because I don't care if it's electronegative. I'm just caring about the atomic number. So the atomic number for fluorine is going to be 9. And the atomic number for iodine is going to be, I believe, 53. And so iodine has a larger atomic number, so that means I'm going to be picking it first, right? So this is number 1, this is number 2, right? Okay, that's what I mean by atomic number. And now I'm going to say carbon heteroatoms. That just means that I prefer a carbon that has, anything but a carbon, anything other than a hydrogen, right? So it could be carbon bromine or carbon nitrogen or even carbon oxygen. And those are a lot better than just carbon, right? So a carbon with a different atom is going to have a higher priority than a carbon with another carbon. Of course, these are going to be increasing in priorities. So first I'm going to look for my atomic number, and then I'm going to go to carbon heteroatoms, right? Priorities, if I spell that right. And finally, we have that a CH3, or let's see, a CH is a lot better than a CH2, and it's a lot better than a CH3, right? CH3. So like a carbon like this, right? It's going to have more priority than this, and it's going to have a lot more priority than this guy, right? So a carbon that has one H or no H's is going to be more important than a carbon with 2 H's, and that's going to be more important than a carbon that has 3 H's, also known as a methyl group. So keep that in mind when we're going through these practice problems, and I'll kind of bring it up to you when it comes out, right? So be on the lookout. Right. So we're going to be doing a lot of practice problems, and I find it easier if I just kind of like condense everything to one page, right? So pardon the smallness of the molecules, but let's get into it. So we're going to be starting with over here. These are separate molecules, right? So of course pause the video and then try to figure out what the answer is, and then resume the video to see the actual answer, right? So over here, we notice that my hydrogen is in the back, and we have a bromine, so I'm going to put that as number 1, right? As number 1. Now, I'm going to be comparing a CH3 group versus a CH2 group. And CH2 is going to be a lot better than CH3. But how did I get my CH3 group and my CH2 group? Well, over here, that's a CH2. If you can't see that, it's going to be a carbon connected to another carbon with a carbon. So carbon wants 4 bonds, so we're going to say that carbon has 2 H's attached to it. On the other side, this has 3 hydrogens attached to it, and I'd rather have a CH2 than a CH3, right? And so I'm going to be listing my priorities. I'm going to say that this is 2, this is 3, and that's 4, right? So we're going to be going in this direction. If you ever get confused, you can do this, right? We're going in this direction, you see? Or if you work in a different way, that's an R, right? So we're going in a clockwise position, that's an R. If you were to look at a clock and it goes from 12 to 6, you're like, well, that's the right time. That's a correct time. It's clockwise. It's an R, right? So we say that this is R right there. The reason why we put H to be number 4 is because it's the lowest priority. H is number 1 on the periodic table, and you can't get worse than number 1, right? And so we're going to say that this is the lowest priority of the whole group. Okay, and we're going to be erasing a lot of stuff to save some space. All right, let's do this in blue. Now, you're probably wondering, shouldn't I number it? Like, shouldn't this be number 1? Well, no, because alcohol is not important when you're doing stereochemistry, right? What really is important is going to be the bromine. Notice that bromine has a atomic number of 35, and oxygen has an atomic number of 6. So I'd rather have my bromine to be more important, right? So that's 1. This is always 4. Right there, that's 4. And let's see. We're going to be going over here, and we're going to be looking over here, right? Well, this one is a CH2, right? CH2. But this one has an oxygen. And you know, that's a heteroatom. A heteroatom is when a carbon has a different atom attached to it, other than hydrogen and other than carbon. So I'd rather have a carbon with an oxygen than a carbon with a hydrogen. So I'm going to be putting number 2 right there on my my oxygen. So that's 2. This is going to be 3, right? And that's 4. So we're going in this direction. 1, 2, 3, right? It doesn't matter if it looks weird. It's going to go 1, 2, and 3 that way. Okay. If you have a hard time remembering it, it's like this. It's going like that. You see? So my arrow is going in an in a counterclockwise position. So it's going from 6 to 12. And if you were to look at a clock, you know, that's a silly clock if you see it going from 6 to 12. So like, that's a very, very silly you know, clock that you have. And if you don't work like that, then you could just have it like this, you see? So I'm going in this direction. You see? So that's an S, if you remember it like that. So this is an S configuration. Now let's go over here. Now this is a mess right here. This is a mess. But it's not too bad. Let's go for it. This is my Stereocenter. It has 4 different attached molecules. And directly on us is going to be an alcohol, which is an O. So O is better than carbon. So we're going to say that this is number 1, right? Now we're going to move down the line. We're going to be looking over here. Now notice that this guy has 4 bonds. And so how many H's does he have? He doesn't have any H's, right? And so I'd rather have a carbon with no H's. This one has a carbon with 2 H's. And if I don't want any H's, which am I going to prefer? I'm going to prefer this side, yeah? I don't care that this side has an alcohol on it. It's really a tie break when you go down the line inspecting each carbon. So just because the left side has an alcohol doesn't mean I'm going to say, oh yeah, this one is number 2. No, I'm going to look down each molecule or down each carbon down the line. In this case, I'd rather have a C than a CH2. Do you understand? So a carbon without any hydrogens is better than a carbon with hydrogens. It doesn't matter if that carbon with hydrogens leads down a path to alcohol. It doesn't matter. It's really a tie break. And so we're going this way like a clock. That's an R. And so you can say that this is going to be an R configuration. Alright. Now we're over here. What can I do? Well, let's see. We're going to put this as number 1. And this is number 4. And we're going to be comparing these 2 carbons. And, well, that one has an alcohol and this one has an alcohol. So does that go to 3? Or is that one 3? Well, if you were trying to do this, well, I have some bad news for you. You would get in a bit of a hurry, right? Well, it turns out that this molecule is not chiral. It's actually achiral. It's actually achiral. And achiral just means that you have 2 of the same things attached to a carbon. So this carbon molecule right here it's attached to a carbon. That one's attached to a carbon, yeah. But that's not the problem. The problem is that those carbons are attached to an alcohol, and that one is attached to an alcohol. So no matter what you do, you're going to have a plane of symmetry. And a plane of symmetry gives you an achiral molecule, which is not good, right? And so you can't show an R configuration, you cannot show an S configuration. Just because two of the same things are on the molecule means that you're achiral, right? So you can't do anything for that problem. Now we go into this problem right here, yeah, this problem. And what do we start numbering? Do we start numbering this as number 1, 2, and 3? Do I do that? Well, no, because you're kind of ignoring the second rule, right? You're ignoring the first rule. I'd rather have the largest atomic number. Oxygen has a number of, let's see, 8. Sorry, not 6, but 8. So that's number 1. Nitrogen has an atomic number of 7. So it's going to be the second biggest. Carbon is atomic number of 6. Yeah, 6 right there. So that's 3. And then atomic number of hydrogen is just 1. So it's 4. Right? So when you're on the exam, just look at the big periodic table on the wall, and you'll see that oxygen has a larger atomic number, which is 8, compared to everybody else. And so we're going in this direction from 6 to 12. That's correct. So that's an R configuration. That is an R configuration. Okay. All right. Well, let's see over here. We have a stereocenter, or an achiral center, or not achiral, sorry. It's a chiral center. So I'm going to be putting number 1 on this oxygen. And let's do it in blue. It's 1 on oxygen, yeah. And we're going to be looking over here, down the line, right? Just because I see an oxygen doesn't mean I'm going to say, oh yeah, this is 2, and that's 3. No, don't do that. You go down the line, right? Let's say that this is a train, that you're on the train. You're not going to go from the train conductor's cargo or train conductor's space all the way down to the end of the line, right? No, you're not Superman. You can't just jump between carriages. No, you have to go through each carriage one by one to make your way down the line to find your room. You're not just going to magically jump to your room, skipping everything, right? No. So you can consider these carbons as carriages, right? So you have to go through each carbon to get to your room. That's how I think of it. Well, I just made it up just now, but I hope that makes sense to you. So we're going to go down the line of this train. We're going to be comparing a CH. Why is that a CH? Well, you have 1, 2, 3 bonds. Carbon wants 4 bonds. So you say that carbon is going to have 1 H right there. So you're comparing a CH2, which is this guy. You're comparing it versus a CH. And what am I going to prefer? I'm going to prefer the CH. So I'm going to say that's number 2, that's number 3, and this is going to be number 4, because hydrogen is like the lowest priority. And so we go like this, right? Which is 12 to 6, that's a correct way, that's R, or like this, R, okay? Whichever makes you happy. That's, I didn't mean to do that, but okay. Let's see, 2, 3, so that's an R. All right, now that's a mess right there. That's a huge mess, but we'll work through it. All right, so first of all, I'm gonna be focusing on this guy, and let's do it in pink too, because I like it. All right, so we're gonna be focusing on this guy, and we have 1. Yeah, we have 1. But when am I gonna go? Am I gonna go over here and there? Well, not necessarily. Instead, I'm gonna go to here, because oxygen has a higher atomic number than nitrogen. So that's gonna be 3, and that's gonna be 4. So we're going from 1, 2, 3. 12 to 6, going left? That doesn't make any sense to me, so that's kind of silly, right? That's pretty silly. We're going to say that this Stereocenter is an S configuration. That's an S configuration, okay? All right. But notice that there's also going to be another stereocenter. There's another stereocenter, okay? So what is it? Well, it's going to be over here. Also notice that this wedge doesn't have anything. When a wedge doesn't have anything, it's going to be classified as a methyl group. The reason why this is classified as a methyl group is because carbons are implied. You remember? Carbons are implied. And so whenever you see an empty hash or wedge, it's implying that there's a carbon there, and that's a methyl group, right? Okay, so instead of having all these pink, we're going to do it in this nice blue, so you don't get confused. We're going to start directly attached to our carbon. So that's going to be number 1, usually it is. And now I'm going to go down the line over here, and I'm going to be looking over there. Do I prefer a carbon with what? With no hydrogens? Or a carbon with 2 hydrogens? Well, I'm going to prefer the carbon that has a lot of things attached to it. In this case, it's going to be on my left. Notice that my carbon has an alcohol, a hydrogen, it's double bonded, this bond and that bond, yeah. Well, not double bonded, but it has 2 bonds. And so it doesn't have any hydrogens, technically, right? It's not CH2, it's not CH3, it's just carbon. And you know, I'd rather have that. So we're going to say 2, and then that's 3, right? But then what's going to be my lowest priority? So let's do it. 2, 3. So we're comparing a we have a nitrogen, a carbon with 2 hydrogens, and then we have a methyl group. And a methyl group, remember, has a CH3. So that has 4 methyl groups, or 4 hydrogens, right? So it's nitrogen versus a carbon versus CH2 versus CH3, you see. And we're going in this direction, it's 1, 2, and 3. See, 1, 2, and 3. So from 6 to 12, going the right direction, that's the right way, so it's R. It's R. R. Okay. Let me just write that down. It's R. Oops, sorry. And let's do it in pink. So you had 2 stereocenters. One was S configuration, and this one right here with the N is going to be an R configuration. It's going to be R configuration. All right, moving on. We have, we're going to do this in the baby blue. We have this heavy molecule. Well, you start down the line, right? Whenever you see a lot of mess in the molecule, just start from one end and make your way down the other end, right? So really imagine that you're on a train and you have to go through each cabin, right? Just take your time. That's all I have to say. Okay, so we have a hydrogen, a methyl group, a carbon with 2 H's, and then a carbon with an alcohol, right? So they're completely different. That is a stereocenter, right? What am I going to say first? I'm going to say that, well, methyl group is not as good as an alcohol, because alcohol has an oxygen, and so I'm going to say that an oxygen has more priority. So I'm going to say that this is number 1. And now we have a CH2 versus a CH3. I'm going to go with the CH2. So I'm going to say that this is 2. That's 3. And that's 4, right? And we go like this from 6 to 12. That's an S. You see, it's a counterclockwise position. So that's an S center. We're going to say that this is S, and we're going to do it in red. Okay. Let's do this in pink. Now, usually, notice that usually my stereocenters are going to be in an area that has a wedge and a hash, okay? It's not in the area like this. My stereocenter is not usually in an area that has no wedge or hash. Usually, wedges and hashes are explicitly shown to you. That means they are obviously shown to you. In this case, we have a a hydrogen and a nitrogen right there. So we're going to see if that's a stereocenter. Let's see. We have a nitrogen, a hydrogen, a CH2, and then we have a C, because that has 4 things attached to it. This carbon has a methyl group, a hydrogen, a carbon, and another carbon. Okay, so it is a stereocenter. So what do we say? Well, we say, well, it's a nitrogen being compared to a carbon with 2 hydrogens and then a carbon. So I'm going to say that this is number 1, right? That's number 1. And then we have a carbon. It has 4 things attached to it, so it has no hydrogens. It's just going to be a carbon compared to a CH2. So I'm going to go with that being 2, this being 3, and that's 4. Okay, so that's 4. We're going this way. And that's very silly. It's counterclockwise, so it's going to be another S configuration. It's going to be another S configuration. And let's do that in red so it pops out. This stereocenter right here is an S. Where can I write it? I'm going to say that this is S, right? Okay. Now we're going to go to the final stereocenter, if there is one. Okay. Well, that carbon has another carbon, and then it has a double bond. Okay. Well, it's kind of confusing, but it is a stereocenter. Why? Well, this carbon, yeah, it has 4 things attached to it, but one of those things is an oxygen. And that makes it different from a carbon that has 4 things attached to it, one of them being a nitrogen. So it's pretty different. Okay, it's pretty different. All right. Well, what do we do? Well, whenever you have an oxygen double bonded to a carbon, you can consider it as an oxygen, or sorry, as a carbon with 2 oxygens. Even though there are not 2 oxygens, you can consider it as being so, right? As if you remember in lecture, professor said that a double bond for oxygen or a double bond to nitrogen means that you technically have 2 nitrogens or 2 oxygens. And so that's really important to me. So I'm going to say that this for sure is going to be priority number 1, right? Priority number 1. I'm going to go back to my carbon, and I'd rather have a what? I'd rather have a nitrogen, right? Rather have a nitrogen compared to a methyl group. I already used up this area, so I'm going to go to my left, and I'm going to say I'd rather prefer a carbon with a nitrogen than a methyl group. So that's going to be 3. That's 4. So we go 1, 2, 3, right? 4. And that's the correct way a clock works. So I'm going to say that this is an R configuration. Okay. So again, it's pretty messy, but it's going to be SSR in order. SSR. Okay. Again, just work your way from left to right, judging if something is a stereocenter versus something that's not a stereocenter, right? You just have to make sure that you're going from left to right, taking your time. All right. Now we're going to go from left to right. Let's see here. Is this a stereocenter? Well, I would say that it's not. Why? Well, you have this carbon, it has an implied methyl group. So that's a CH3. And then this carbon also has a carbon. Sorry, this carbon also has a methyl group. So you have a methyl group, Me, attached to a carbon that has an Me and a hydrogen. Is that a stereocenter? Is that chiral? I wouldn't say that it's chiral because it has 2 of the same things, and that makes it achiral. So we can just ignore it. We're going to move on. Okay. This is not a chiral center. It usually isn't because it doesn't have hashes or wedges. So we're going to move on. This one too. Pretty bad. What about this one? Well, that one has the same problem as its brother. It has a methyl group, and then over here it has an implied methyl group. And so you can't have a chiral center. Also notice that we are symmetrical. If we're symmetrical, then we're going to be achiral instinctively. So we're going to say that this is actually achiral, not chiral. It's a bad molecule. Okay, moving on. We have kind of like a cyclohexane. right? And, you know, these are pretty tough. Well, what do I do, right? Well, it's hard to see the difference. Sometimes you have a CH2 and that's a CH2. Okay, that's a CH2, but that has a carbon with a hydrogen and a chlorine. And, you know, that's different from a carbon that has just two H's, right? So the way I see it, since it's the last problem for the page, I'm going to go all out explaining it, right? We're going to say that this is what you have, a carbon with a carbon and another carbon. So that's 6 carbons. This one has a hydrogen and a alcohol, right? And then we have this guy. Okay, so here's the difference. We have 2 carbons that are possible chiral centers. Okay, they're possible. But here's the difference. This carbon is attached to 2 hydrogens, and so is this carbon with 2 hydrogens. Okay, so we're going to go down to the other caboose. We're going to go down to the other cabin in the train. This carbon is different from this carbon. Notice that this carbon right here has a hydrogen and a chlorine, but this guy right here has a hydrogen and another hydrogen, and so they're different. Therefore, they have to be chiral molecules, right? They have to be chiral molecules. You know, if this weren't here, then this would not be chiral, because you have 2 of the same things. You would have a CH2 and a CH2 and nothing else, and that's different, or that's the same. However, since this guy exists, technically this path is different, right? This path takes you on a CH2, but this path takes you to CH2, 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 right? So it's a completely different path to get to the same area. Therefore, we can say that these are 2 different molecules, and therefore we can say that that is chiral, right? So very complicated, but you just have to see it, that these are completely different pathways. All right. So since we already made this model, we can just work on it. On my stereocenter number 1, we have 2 stereocenters, right? We can say that this is what? Priority number 1, since it's an oxygen. And we have a CH2 right there. So I'm going to go like this. Why did it pick that pathway? Well, I'd rather pick the pathway that gets me to the other chiral center, the shortest, right? So I'm not going to say, oh yeah, this is 2. Why would I take the longest path? I'm going to take the shortest path, right? It's different. And then I'm going to take my shortest path if I can, since I have no choice. So I'm going to say that that's 4. So we have a 1, 2, 3. And that's, what? That's R, right? So you're going to be, oh yeah, that's R. But hey, notice something. You got to notice something. Keep your eyes peeled for this. This hydrogen is in the front. And that's bad. You always want to do stereochemistry with the hydrogen or your lowest priority group in the back. Sometimes your lowest priority group is not hydrogen. So whatever is your lowest priority group, whatever is number 4, has to be in the back. If it's not in the back, you can just reverse what you did. So we said that this section is over here, right? Oh, and that's R. Well, since my lowest priority group, which is hydrogen in this case, is in the front, we're going to have to reverse it. So we're going to say that this is going this way, right? Oh, sorry. That it's going this way. Okay, so all I did was I put my arrowhead on the opposite direction. So it's an S configuration. That's S. Okay. On the other molecule, we're going to say that this is priority number 1. This is priority number 2, right? So it's number 2. That's my shortest path. This is my longest path, 3. This is going to be 4. So we go 1, 2, 3. Oh, that's S. But then you have to realize that hydrogen is in the front, so you're going to have to reverse it. Instead, it's going to be this way, right? So it's going to be what? R. It's going to be R. So that is R. And so we say that this is S and R. On the next couple of problems, we're going to speed it up, so I'm not taking like 30 minutes of your life, right? So now you understand the basics of what to do, and we're just going to be crushing these examples. All right, let's get to it. For this one, we're going to do, this is priority number 1, this is 4, that's 2 and 3. 2 because that's a CH2 being compared to a CH3, so we're going to go this way, 1, 2, and 3. Well, that's an R, yeah, that's an R configuration. But notice that my hydrogen is in the front this time, so instead of going this way, we're just going to flip the arrowhead that way. And so that's an S configuration. This is S. Okay. Now we're going to be going over here. 1, well, that's 1, 2, 3. That's a CH bond being compared to a CH2. We just go down the line. So that's 2. 3 and 4. The H is in the back. It doesn't matter if the H is with oxygen. You know, that's an alcohol. It's completely different from the hydrogen. So the hydrogen is going the backwards. So we just say it's this. So it's an R configuration. Right? It's R configuration. Okay. I hope you're liking the speed, right? We're picking this up. Alright, so now we're kind of in like a mess. This right here is never a stereocenter by itself. It's never a stereocenter, so you could just ignore it. This one has 2 of the same groups attached to the same carbon, so that's not a stereocenter. Most likely the stereocenter is right here. Right? Okay, so what is it? We're going to say that this is number 1. This is going to be 4. We're going to go down over here and over here. So that's a C. Right? Notice that there are 4 bonds to that carbon, so that's a C being compared to a nitrogen. Well, you're going to say, oh, well, this is 2, and that's 3. Well, that's wrong. Why is it wrong? You're failing to recognize that the order of priority is atomic number. And then afterwards, we go to what? Carbon heteroatoms. And then carbon-carbon or carbon hydrogens. So a carbon heteroatom is just a carbon that has something attached to it. In this case, this would be acting as a carbon heteroatom, right? That carbon has the nitrogen attached to it. This carbon only has carbons attached to it. And so what am I going to prefer? The carbon with something attached to it. In this case, nitrogen. I'm going to say that this is number 2, and that's 3. I don't care about this. I'm not going to that cabin yet. I'm still going in cabin 2, right? So in my train, I have to go through each cabin first. I can't just jump over there, right? So we're going to say, also the hydrogen is in the back, so proceed as normal. We have 1, 2, 3. That's R configuration. So R configuration. Okay. Over here, do this in nice baby blue. Over here. Well, let's see. This is number 4. Is this number 1 or is that number 1? Oh gosh, I can't decide. It's like they're 2 of the same things. Well, they are 2 of the same things. That's pretty bad. That's actually achiral. You cannot have a molecule that has 2 of the same things attached to it and say that it's chiral. It's actually achiral. It also has a plane of symmetry, so that's going to be achiral. I'm just going to say that's AC, right? Okay. And what about this one? Well, over here we have number 1. It's an oxygen. It's directly attached to us, so it's going to be like the first guy. Now I have to compare an oxygen with a nitrogen. What am I going to choose? I'm going to choose the oxygen first because it has a higher atomic number. So that's 2. This is going to be 3. And that's 4. Hydrogen is in the back, so we proceed as normal. That's 1, 2, and 3. That's a very silly curve. So that's a very silly curve. We're going to say that this is S, right? That's S. And first of all, we're going to erase this guy. Okay, cool. What about this one? Well, you're probably tempted to say that these are that these are the same molecule, but they're not. They're actually different. Notice that they has a double bond and this does not, so they're different. Okay. Well, this one has an oxygen first, so I'm going to say that this is number 1. This has to be number 4. Then we go over here. Now this is a CH. Well, this is a CH compared to a C. Notice that this carbon has 3 bonds and that carbon has 4 bonds attached to it. So I'd rather have this carbon second than a carbon third. So that's a C compared to a CH. I'd rather have the C. Alright, so we're going to go this way. But notice that my hydrogen is in the front. So I have to reverse it. That just means putting your arrowhead over here. And that's a very silly curve. It goes like this. Right? Or it goes like counterclockwise. So you can say that that is S configuration. Right? S configuration. Now, always look at your areas like this that has a hash and a wedge. That usually is a stereocenter. Usually, sometimes. Alright, let's look. This is going to be number 1. Then we're going to be over here. Over here. Well, which one am I going to pick? Am I going to pick the carbon with a nitrogen or a carbon with an oxygen? That's right, I'm going to pick the carbon with the oxygen. So I'm going to say that this is number 2. That has to be 3. And that's 4. Alright, for that center, we're going to say that is going like this. 1, 2, and 3. The H is in the back, so that's clockwise. That's going to be R. R configuration. For the first one. That's R. Okay. For the second center, what is it? For the second center, let's do it in pink. We have an oxygen right there, that's 1. And let's see, a CH2 compared to a C. What am I going to pick? Well, I'd rather have the C. The C has 4 things attached to it, that being a hydrogen, a carbon, an alcohol, and another carbon. So that has 4 bonds. It's just a C being compared to a CH2. So I'd rather have the C first, right? Or second. So it's going to be 2, 3, and then 4. Notice that this wedge, or this hash, is empty, so it's going to be a methyl group. So yeah, a CH2 is better than a methyl group, right? Methyl group is this CH3, okay? And the hydrogen, well, there is no hydrogen. The lowest priority group is going to be in the back, so proceed as normal. So it's 1, 2, and 3. That's clockwise. That's going to be what? Yet another R configuration. That's going to be R. Okay. Pretty cool. If you do a lot of them, you technically you get used to it. So that's good. Let's do it in red. Let's see. Well, we have a nitrogen right here. We're going to go over here. That's 3 bonds, so that's a CH, right? So that's going to be number 2. That's a 3, and that's a 4. Hey, wait a minute. You're probably wondering, well, dude, there's like an H not behind me and it's not in front of me. What do I do? I'm freaking out. Well, don't worry about it. Let's rewrite the molecule, because that's a pretty good example. Right? Whenever you have a hydrogen or your lowest priority group not on a wedge or not on a hash, it's like this, right? Whenever you have that happening, you have to put the H to whatever is in the back. You have to exchange it. So in this case, my back atom or molecule is going to be a methyl group, but my hydrogen is right there. So I'm going to exchange my hydrogen with the methyl group with whatever was in the back, and we're going to put our methyl group right there. So to be obvious, I'm going to put CH3, right? So all I did was I put my hydrogen where my methyl group was. My methyl group was in the back. I'm not going to put it forward. I repeat, I am not going to put my hydrogen in the front. I am going to put my hydrogen in the back. That means I have to exchange, okay? Right, so now we assign priority as normal. That's going to be 1, 2, 3, and 4. It's going to be 1, 2, and 3. Oh, so that's an S configuration. However, stop. Since you exchanged your hydrogen, you changed the direction, you're going to have to reverse what you did. So instead of having S, right, we're going to have this guy. So it's going to be in that direction. It's going to be R, all right? So be very careful, all right? For a recap, whenever your lowest priority group is not on a wedge or hydrogen, you're going to have to do what? Whenever your lowest priority group was not on a wedge or hash, you're going to have to exchange it with whatever is going in the back, then assign priority, and then after you assign a priority, reverse what you did. So if you got an R, you're going to have an S. If you have an S, you're going to have an R, right? This also is prevalent in this example. So let's do it. Let's see here. This is not chiral for this section. That's a CH3 with a CH3. So we're going to ignore that one. We're going to move on to the next cabin in the train. Well, we have a CH3 and an alcohol. Then we have a carbon. So that's a chiral. So we're going to say 1, 2, 2, 3. But notice that this hydrogen is not on a wedge or hash, so we're going to have to redraw it. That's perfectly fine for me. Let's do it over here. Right. Okay. And let's see here. This is still a methyl group. It's in the front, we don't care. However, I'm going to put my hydrogen in the back, and then my alcohol where my hydrogen was, and we're going to assign priority. This is going to be number 1, this is number 2, 3, and 4. So it's going to do this 1, 2, 3. Okay, so that's counterclockwise, that's S, but then I have to reverse it because I changed my hydrogen. So I had an S, now I'm going to have an R configuration. So I'm going to have an R configuration. Okay. For this one, what do we have? Well, we have, for sure, it's chiral, right? This is going to be number 4. That is a, do I want to go here or do I want to go there? I'd rather go to my oxygen first. So that's going to be number 1. Then a CH2, that's 2, and that's 3. So it's going to do 1, 2, and 3. So, you know, he's very happy. He's very happy. So that's R configuration. That's a clockwise configuration. So it's going to be R, right? That's a very bad R. All right. For this one, we're going to start over here. That's 1. That's a CH3 group compared to a CH2. I'd rather have CH2. That's 2. That's 3, and that's 4. Notice that hydrogen is in the front, so we're going to have to reverse what we do. That's 1, 2, 3. That's going to be R configuration, but then a hydrogen is in the front, so we're going to put it over there. That's an S configuration, right? That's an S configuration. S. Right. Over here on this problem, we have what? Well, I'm instinctively going to be focusing on this guy. They usually are stereocenters. That's going to be 1. We're going to go down the line. And you know, I'd rather have an oxygen than a carbon, right? So that's a this is a CH2 with a alcohol, and that's just a C. So I'd rather have the alcohol first because it has a higher atomic number. Okay, so that's going to be 2, 3, and 4. All right, so it's like this, 1, 2, and 3. That's S configuration as well. Okay, so that's going to be S. Over here, we have an alcohol, that's 1, that's going to be 4. Let's do that in a different color. It's going to be 1, 4. We're going to go down this line and that one. So that's a CH2 being compared to what? That's 3 bonds, 1, 2, 3 bonds, so that's an H. So that's a CH versus a CH2. I'd rather have a CH, right? So that's 3, 4. Alright, so it's the same thing. It's going to be S. That's 1, 2, 3. It's S configuration. Right. On this one, you're probably saying, oh, you know, this is a chiral, but no, it's not, because this oxygen has an ethyl group, 1, 2, 2 carbons. That's an ethyl group, and this one has a cyclohexane group attached to it. So these are different molecules, right? Now the problem is, you know, which one am I going to prefer? Well, I'd rather have the cyclohexane group attached to me. So it's going to be number 1. This is going to be 2, 3, and 4. Right? So, you know, I'd rather have a large substituent than a small substituent. So this is a 1, 2, 3. That's what? An S configuration as well. Pretty freaky, right? Pretty weird. That's an S configuration. Over here, let's do it in green, or is this baby blue? Right. Okay, so let's see. That's 1. Am I gonna have what? This group right here that has a carbon with an alcohol, or am I gonna prefer two oxygens? Which one? Well, you know, I'd rather prefer a double bonded oxygen, because technically that counts as 2 oxygens, and I'd rather have 2 oxygens than 1 oxygen, right? So I'm going to do 1, 2, 3, and 4. And again, that's going to be 1, 2, 3. That's an S configuration. Weird, right? Over here we have CH2 and CH2 versus a CH3. You know, for sure I'm going to have 4, and this is going to be 3, right? So CH2 and CH2, not good. CH2 versus CH2, that's not good either. And then CH3 versus a CH2, which one am I going to prefer? Well, I'd prefer the CH2, right? So I'm going to do, this is 2, and that's, this is number 1, and that's 2. So a CH2 beats a CH3, and that beats a CH3 as well. So, I mean, it's kind of confusing, but just go down the line, right? So I'd rather have a CH2 first, because all I have is carbons and hydrogens. So I'm going to do, going down the line, this is the same, that's the same, this is the same, that's the same. This is CH2, and that's a CH3. I'd rather have this guy than that guy, right? So, it's just how you number it. So let's go 1, 2, 3, and 4. That's an S configuration as well. S configuration. Alright. Over here, what do we have? Oh man, my hydrogen is not on a wedge or hash. Hydrogen is the lowest priority group. My lowest priority group is not on a hash or wedge, so I'm going to redraw it. Okay. Okay. So all I have to do is just put my H with, exchange my H with whatever was in the back. In this case, bromine was in the back, so I exchanged it, right? So now we assign priority. This is going to be number 1, 2, 3, and 4. So we go 1, 2, 3. Oh, you know, that's an S configuration, right? But we exchanged the H, so we're going to have to reverse it. So instead of having an S configuration, we're going to have a what? An R configuration. Okay, so that's an R configuration. Just make sure that you're exchanging your H with whatever's in the back, and then afterwards you reverse your notation. So if you had an S, you're going to have an R. If you had an R, you're going to have an S, right? Okay. Right here, we have, in this Stereocenter, we are comparing a CH2 with another one. So we're going to move down the line. That's a CH3 compared to a CH2. Sorry. So I'd rather go that way first. 1, 2, and then 3, 4. You see? Okay. So let's go 1, 2, 3. And that's R configuration. That's R configuration. over here, well, man, we're gonna have to redraw this because my H is not on a wedge or hash. So let's cut this, right? Oh man, these are always hard for me to do. Let's see, like this. So I'm going to exchange with my hydrogen. I'm going to put my hydrogen in the back. My alcohol was in the back, so I'm going to put it in the front. Now we're going to assign priority. This is number 1, 2, 3, and 4, right? Okay, so that's 1, 2, 3, and 4. We have 1, 2, 3. That's an R configuration, but the hydrogen was moved, so we're going to move our line. We're going to say that this is what? That this is an S configuration. So that's an S configuration. Okay, that's S. So we're going to say R and S. Okay, let's do it over here. All right, let's see. Well, for here, we have an oxygen, so let's say that that's number 1. We're going to go over here. And what am I going to prefer? Am I going to prefer the carbon with 4 bonds or the carbon with 3 bonds? Well, I'm going to prefer the carbon with 4 bonds. So I'm going to say that that's number 2, that's 3, this is going to be 4. Okay, so that's an S center. All right, now this one. Oh man, this one is a doozy. It's spectacular, really. I'm gonna need all my colors. Okay. Alright, so I redrew it, so it's kind of blown up now. Let's focus on the top one first. Why are we focusing on the top one first? Well, the top one is it's closer to the oxygen. So we're gonna say that this is gonna be priority number 1 for red. And then you're probably wondering, oh, you know, this is 2. No, that's not 2. Why? Well, you have a CH2 connected to that alcohol. And you know, I'd rather have an alcohol by itself with a carbon. So yeah, that carbon has an alcohol, but it doesn't have 2 other hydrogens, right? So I'm going to say that this is number 2. Then that one is going to be number 3, and that's going to be 4. So to save ink, we're just going to say that this is going to be right here. That's 1, 2, 3, right? Hydrogen is in the back. So what is that? That's going to be an R configuration. That is an R configuration. Let's go to the next one. Well, I'd rather have what? A number 1 right there. Yeah. I'd rather have a number 1. This is going to be number 2. Right? And what else are we going to have? Well, you know, well, hold on. Hold on. My mistake. I'd rather have 1, 2. Why? Well, if I went 1, 2 over here, then I'm saying that this is more important than just a carbon with an oxygen. And that's not true. You know, I'd rather have an oxygen attached to a carbon just by itself. So I'm going to say 1, 2. And then this is going to be 3 and 4. So to save space, we're going to say that this is a 1, 2, and 3, right? So 1, 2, and 3 is going that way. So that's an S configuration. It's an S configuration. However, you have to notice that your hydrogen is in the front, right? So again, this is a 1, 2, 3, 4. So 1, 2, 3. S configuration, but your hydrogen is in the front, so you're going to have to reverse what you did. It's going to be an R configuration. Okay. In this Stereocenter, this is going to be number 1. These two are the same. Okay, so we're going to go over here, right? Oh, that's an OH, by the way. So yeah, this is the same as this guy. So we're going to go to the next cabin. We're comparing this guy with this guy. And what do I prefer? Well, I'd rather prefer the, what? The alcohol, right? So I'm going to say that this is number 2, this is going to be 3, and that's going to be 4. So it's 1, 2, 3. hydrogen is in the back, so for sure that's an S configuration. That's an S configuration. Alright, and this stereocenter, let's start doing it in blue. This stereocenter, this is going to be number 1 right there. Okay, so we have 2 of the same guys, right? So we're going to go to the next guy. This guy versus an oxygen. What am I going to prefer? I prefer the oxygen, right? So we're going to say that this is 2, this is going to be 3, and that's 4. So we have a 1, 2, 3. Oh, it's an S, but the hydrogen is in the front, so we're going to have to reverse what we did. Put your arrowhead right there. That's going to be an R configuration. That is an R configuration, right? Okay, so wait, hold on. Let's do this. Let's see. That's 1, 2, 3, 4. Sorry, hold on. Make sure this is right. 1, 2, 3, and 4. So it's going to be this way. That's what? S configuration, but right? S configuration, and then we're going to reverse it. So it's going to be R configuration. Should be, yeah. It's going to be R configuration. Okay, so now we're dealing with what? This guy. That's going to be number 1. Well, we're going to go over here, and we're going to be comparing this guy. I'd rather have an oxygen by itself, so that's going to be number 2, right? This is going to be number 3, and that's going to be number 4. So it's 1, 2, 3. 1, 2, 3, that's counterclockwise, H is in the back, that's going to be S configuration, yeah? Now hold on, that's not true. It's not true because I made a mistake. What was my mistake? My mistake was that I instinctively saw an alcohol and I was like, oh yeah, that's high priority. But you know, I'd rather have an oxygen by itself. I'd rather have an oxygen by itself. So I'm going to say that this is number 1. This is number 2. That's going to be number 3. And that's 4. So it's 1, 2, 3. Right? That's going to be an R configuration. Why? Because yes, this alcohol is attached to this carbon. However, this carbon right here that has, this oxygen is directly attached to this carbon. If you can't see it, it's like this. And then this guy has an alcohol and then an H right there. And so what do I prefer? An oxygen by itself or an oxygen with a hydrogen? Well, I'd rather have an oxygen by itself, right? So I'm going to say that that is going to be priority number 1, right? So don't make the mistake that I did. Always, double check what you had. So that's going to be an R configuration. We're going to do some more practice problems later on, right? So get ready. All right. Well, we will start doing the second part of the questions, right? So sometimes you're going to have a meso compound, and sometimes you're going to have a chiral center or an achiral center. So for these problems, I want you to say if it's chiral, achiral, or if it's meso, right? Okay, so for the first one, it's just a simple chiral center, right? An oxygen is different from a nitrogen, that's different from a methyl group, and it's different from a hydrogen. So we're going to do 1, 2, 3, and 4. The H is in the back, so that is a what? That is a R, right? It's going to be an R center. For the second one, this is going to be achiral. It's not chiral because you have 2 of the same things attached to the carbon, right? So that's going to be achiral. Achiral. All right. What about this one? Well, you have an hydrogen, you have an alcohol, then you have some carbons right there. So it looks pretty good, right? However, we have a plane of symmetry. And it's pretty obvious because you have 2 of the same things. You have 2 carbons on the left side and you have 2 carbons on the right side. So even though we were potentially chiral, right, a plane of symmetry makes you achiral. So if you have a plane of symmetry, that means that you are achiral, right? So that is achiral. What about this one? Well, let's see. It looks pretty good, right? However, if you notice something, there is a plane of symmetry. This chlorine is in the front, and this chlorine is in the front as well, right? So these two chlorines are in the front. You can actually split them in half, the molecule in half, and you can fold it together. If you can fold them together, then what? You end up getting something that's achiral. It's achiral because you have a plane of symmetry. So this is also achiral. What about this one? No, it's not too obvious, but we're going to have to redraw it. So whenever you have something that's kind of like twisted, where a chlorine or whatever is upwards and the whatever group is downwards, right? So let me rephrase it. If you have something that is going upwards and something that is going downwards and it's a single bond, then you could just twist it, and that's what you want to do. You want to get so that everything on your molecule is in the same plane, right? So if you're confused, try twisting the molecule. Alright. Whatever was in the back is going to be in the front. So this chlorine is going to be in the front, and this hydrogen is going to be in the back. If you don't believe me, try it with your model kit. Now, do you see something? We have a chlorine going in the front, and we have a chlorine going in the front as well. And that means that it has a plane of symmetry. And if something has a plane of symmetry, it's going to be achiral. Right? It's going to be achiral. So what we learned from that problem is that sometimes you're going to have to kind of rotate the molecule by one bond to get it in the same plane, right? And it just makes the question a lot easier. You can only do that if it's a single bond. Double bonds and triple bonds cannot rotate, okay? But what about this one? You think it's a plane of symmetry? Well, I don't think so, because you have a methyl group. Or you could think about it as an isopropyl group. So yeah, for sure, that right there is an isopropyl group. Not good, not cool. Alright, so we can actually show a chiral center. So that's a chiral center right there. And that's a chiral center right there. We have 4 different things attached to us, right? Okay. So let's try to find the chirality, or priority. So we're going to be focusing on the left side and then make our way to the right side. Chlorine is going to be number 1. And this is CH3 right there. And this is a carbon, because that carbon has 4 things attached to it. It has a hydrogen, a chlorine, and then a bond on each side. So I'd rather go right there, right? I'd rather go 1, 2, and let's actually do this in a different color. So I'd rather go chlorine first because of the atomic number, and then the carbon with no hydrogens on it, right? And then a methyl group and a hydrogen. That hydrogen is in the back, so it's going to be like this, right? 1, 2, and 3. So that is what? That is the R configuration. Okay, that's the R configuration. Now, what about the right side? Let's see, 1. Am I going to do a carbon with a chlorine, or am I going to do a carbon with a hydrogen, right? So what I'm trying to say is, am I going to pick this center, or am I going to pick this center? Do I want something that has a chlorine, or do I want something that has a carbon? Well, I want to pick the carbon that has a chlorine with it, right? So I'm going to say that this is 2, this is 3, and that's 4. The hydrogen is in the back, so it is what? 1, 2, and 3. Alright, so that's going to be an S configuration. S configuration. So for in total, we have an RS center. RS center. Alright. Now what about this one? Well, I hope you can see that this is actually going to have a plane of symmetry. And if it has a plane of symmetry, it's going to be achiral. Well, I butchered that, but it's AC, achiral, right? And what about this guy right here, this cyclohexane? What do I do about that? Well, let's see. We have something that's going upwards, so we're going to say that this is up. We have something going upwards right here, so this is also up, right? And the way you can translate it to a normal cyclohexane is you draw it, right? So we're going to do a cyclohexane, right? And this right here, this middle group is this guy. And whatever is up is going to be in a wedge. Right, so we have an alcohol right there and an alcohol right there. And over here is going to be an H. Whatever is down is going to be in a wedge. Or not wedge, but dashes, sorry. So whatever's going downwards is going to be dashes, and whatever is going upwards is going to be a wedge. And you can see here, if you translate it, you're going to have a plane of symmetry. And so this is called a meso compound. It's also achiral. Right? So this right here is meso. Right? And what else was meso? This would be meso as well. If it has symmetry, it's most likely meso compound. Right? So it's achiral, it's going to be meso with a plane of symmetry. What I'm trying to say is, if a molecule is achiral because it has a plane of symmetry, then that molecule is going to be called a meso compound, right? So if this did not have symmetry, we would be chiral. But because this has symmetry, it's going to be achiral, and we call that a meso as well, right? So yeah, that's pretty cool, right? We're going to do some more practice problems right now. All right, over here, what do I want to do? Well, do I want a number? Do I want an oxygen, or do I want a nitrogen? Well, I'd rather have an oxygen first, right? Okay, and then this is a carbon with an alcohol, and that's a carbon with a nitrogen. So they're completely different things, right? They're completely different. So I want the oxygen first. It has a higher atomic number, so I go 1, 2, 3, and 4. So it's 1, 2, 3. The H is in the back, so we keep it the same. That's an S, right? Now you're probably thinking, this may be, this may have a plane of symmetry. Well, it doesn't, because right here you have a double bond, and over here you do not have a double bond, and so that cannot have a plane of symmetry, right? We start at the oxygen first, so that's 1. Now let's see, 1, 2, 3, 4. That carbon has 4 bonds, therefore it doesn't have any hydrogens. I want that second. This one has 3 bonds, it's going to have a hydrogen. That means it's going to be 3, and that's 4. So we go 1, 2, 3, 4. But notice that you have a hydrogen in the front, so it's going to be reversed. And that means that we're going in a what? An S configuration, right? Okay. Over here, again, you would think that it has a plane of symmetry, but this one has a double bond, and this one does not have a double bond. All right, so we begin at oxygen. I'm going to do this 3-bonded carbon, which just has 1 H attached to it, so that's going to be 2, compared to a carbon with 2 hydrogens on it. That's going to be 3, and that's 4. So 1, 2, 3. Well, is going in the counterclockwise position, right? Counterclockwise. Let's see, so that's going to be S, I would say. Let's double check. So 12 to 6, that's going to be S. Yeah. Let's double check. 1, 2, and 3. Yep, that's right. Okay. What about this one? Oh, we can just separate that. No, you can't. Why can't you do that? Well, notice that right here, this chlorine is on the wedge, and over here, this chlorine is in the hash marks, right? So this cannot be. This does not have a plane of symmetry. If you were to fold it, it would not be correct, right? So you know, if you have something that's going on a wedge and then the other thing is going on a hash and they have the same atom, in this case if chlorine is on a wedge and chlorine is on the hash on the other one, well, they're not the same, right? And so you can't fold them no matter what and, you know, get a meso compound. That's not possible. That's not possible here. So because you can't fold them in half, they are going to be chiral. They're going to be chiral. All we have to do now is just find the priorities. So chlorine is going to be number 1 for this stereocenter. There are 2 stereocenters. Alright. So chlorine is going to be number 1. And I'd rather have a carbon with 4 things attached to it than a methyl group. So I'm going to say that's going to be 2, right? This is 3 and 4. Hydrogen is in the back, so it's 1, 2, 3. That's going to be the correct way, so that's R. If we go to the second one, chlorine is in the back, so it's 1, 2, 3, and 4, so it's this way, 1, 2, 3. But then hydrogen is going to be in the front, so we have to change our arrowhead, right? So it's going from 6 to 12, that's the correct way, that's going to be R. It's going to be an R configuration. R configuration. So for this one, it's just going to be R and R. Alright. Over here, again, if you have something twisted out of contortion, twisted out of the plane, well, I should phrase that better. Whenever you see something like this, right, just twist this guy into the same orientation. So for this guy, we still have a chlorine on the wedge and hydrogen on the hash. Whatever was a wedge will become a hash. Whatever was a hash becomes a wedge. So now the hydrogen is going to be coming outwards, and the chlorine is going to come in inwards, right? Do we have a meso compound? Do we have a plane of symmetry? No, we don't have a plane of symmetry. That's because chlorine is on a wedge, and on the other side it's going to be on a hash. And there's no way that you can fold it so that they really interchange, right? So no matter how we fold it, it's going to be not the same. So this does not have a plane of symmetry. That means that is going to have a chiral center. A chiral center. So let's start prioritizing. Chlorine is going to be number 1. Do I want a CH3 or do I want a carbon that has 4 things attached to it? Well, I want the carbon that has 4 things, yeah? So I'm going to say 1, 2, 3, and 4. So it's 1, 2, 3, 4. The hydrogen is in the back. This is the correct way a clock moves, so that's going to be the right way. That's going to be R, right? That's going to be R. All right, let's do this in pink. We have a chlorine right here. That's number 1. This is going to be 2, 3, and 4. But the hydrogen is in the front, so we're going to have to reverse it in the end. So 1, 2, 3. Okay, I have to reverse it, so I just put my arrowhead right here. That's going to also be in the correct way. A clock moves, so that's going to be the right way. That's R. So over here we have an R and an R. Okay. Do you have a plane of symmetry here? No, you don't, because you have a bromine and a chlorine, and the rest are the same. So this for sure does not have a plane of symmetry. This has 2 chiral centers, yeah? It has 2 chiral centers. So let's say chlorine is going to be number 1 for this chiral center. That's a different chiral center. Let's start on the left side. It doesn't matter if you start on the right side. I like starting on the left side. I'd rather have a carbon with 4 things. That's 2, 3, and 4. But by now you're getting tired of this, right? I would hope so. So this is going to be R configuration. Right. And over here, let's do bromine. That's 1, 2, 3, and 4. So that's 1, 2, 3. Hydrogen is in the back. This is the wrong way a clock moves. That's incorrect. So it's going to be S, right? So really just focus on what a clock moves, right? Okay. Are you saying that this has a meso? That this is a meso compound, or that it has a plane of symmetry? Well, you know, I would argue against it, right? I wouldn't say that it has symmetry. The reason why it's not achiral is because over here you have a alcohol on a wedge, and then on the other side you have an alcohol on hashes, and so you're not gonna really have a wedge and then a wedge inside, right? Because that would be a mirror. You're superimposing them. Superimpose means to put something directly on another thing and they match completely, right? However, if you were to fold this, you have an alcohol and then a wedge. And they're not into each other, right? They're not into each other. So, yay, that's a face. Because these guys are not into each other, they're not inside each other. Like we could have a wedge, and let's do this in blue, and another wedge. That would be good. If we had a, I'm sorry, those are hashes. If we had a wedge like this, and then we had another wedge inside, that's good. That would be symmetrical. However, this is different. First of all, one's a wedge and one's a hash, so automatically they can't be symmetrical, right? And if it's not symmetrical, then it has to be chiral most of the time, right? So now we can just say chiral centers. If you're just given wedges, you know, it's always a good thing to draw out your implied hydrogens right here. So over here I would do some hydrogens, yeah? Okay. So now this is a stereocenter, and this guy right there is a stereocenter as well. All right, so let's erase that really quickly. Okay. I hope you're finding this helpful, right? Okay. This is an oxygen, so we're going to say that this is number 1, right? Do I want something? Do I want a carbon that has 4 things or a carbon that has 2 hydrogens? Well, you know, I'd rather go with the carbon with 4 things. So we're going to say that this is number 2. This has to be 3, and that's 4. So 1, 2, 3. That's the correct way a clock moves. So it's going to be an R configuration. It's going to be an R. Okay. Let's do this in a baby blue. This is going to be number 1. Do I want a carbon with 4 things? Of course, always. It's going to be 2. And this is 3, and that's 4. So it's 1, 2, 3. But notice that this hydrogen is in a wedge. That means this hydrogen is in the front. You're going to have to reverse it, where you put your arrowhead. So my arrowhead was here. I'm going to put my arrowhead in the opposite direction. So that is a correct way a clock moves. That is also going to be R. So for this guy, it's R and R. Okay. And now we're going to be focusing on this guy. Okay. So we have something going upwards, that's the alcohol, and then we have the alcohol going downwards. Okay, so what does that mean? Let's do it over here. First I'm going to draw a cyclohexane. Alright. This guy right here, this peak, is representative of this guy. Okay? Sorry. So we have an alcohol going upwards. That's a hydrogen going downwards. And over here we have an alcohol going downwards and a hydrogen going upwards. Okay. Well, you know, if we had this alcohol going upwards and the other alcohol going upwards, then that would be a achiral molecule. It would be Meso, right? Well, in this case, we have an alcohol going upwards and we have another alcohol going downwards. And, you know, a wedge is different from a hash, and so that's not symmetrical. If it's not symmetrical, then there's a possibility that it could be chiral. In this case, it is chiral, right? So now we're going to be assigning priorities to these 2 different groups. I want to start with the oxygen first, and then the carbon that has 4 things to it, that's going to be 2. That's a carbon with CH2, that's 3. This is going to be 4. So for this top one, it's going to go 1, 2, 3, right? 1, 2, 3, 1, 2, 3, right? And that's the correct way a clock moves. So that's going to be R, right? That's going to be R. And for this bottom one, we start with the oxygen, that's 1. Carbon with 4 things, that's 2. Carbon with 2 hydrogens, that's going to be 3 and 4. So it's going to go 1, 2, and 3. 1, 2, and 3. Well, let's see. 1, 2, and 3. So it's going to be from 11, or from 1 to 6 in the opposite direction, which is not good. That is not good at all, right? Let me just double check, yeah. 1, 2, 3, 4. Yeah, and then this hydrogen is going to reverse what I did. So my hydrogen is going to put it like this. So we're going from 6 to 12. That's the correct way a clock moves. So it's going to be RR as well. It's going to be RR as well. So the top one looks pretty difficult, right? Well, it's not too bad because, again, you have a double bonded oxygen. And whenever you have a double bonded anything, like this could be nitrogen, sulfur, tellurium, doesn't matter. Just count it as having 2 oxygens to that single carbon, right? So you can think of this carbon as having 2 oxygens on it, right? And so, do I want 1 oxygen or do I want 2 oxygens? Well, I want 2 oxygens, right? So I'm going to count this as number 1. And now we have either an alcohol, which is just 1 oxygen, or a carbon that has some oxygens on it. So which one am I going to pick? Well, I'd rather have the carbon that is directly attached to this oxygen. Why is that? Well, this carbon is directly attached to an oxygen, but then it's also attached to another carbon, into another carbon, into another carbon with hydrogens, and there's too many things, right? I'd rather have a carbon with just a straight up oxygen on it. Nothing else, no more, no less, right? And so an oxygen is going to have more priority than just a carbon with an oxygen, with a carbon, with a carbon, with a hydrogen. It's not so good. So yeah, for sure this is going to be number 3. Hydrogen is always number 4, or it's typically the lowest priority group, right? Sometimes your lowest priority group is not hydrogen. Sometimes it could be fluorine or it could be iodine. Just keep on the lookout for your lowest priority group. Make sure that it's in the back. In this case, hydrogen, which is our lowest priority group, is in the back. Therefore, we can proceed as normally. So it's going to say 1, 2, and 3. Okay, that's the correct way a clock moves, so it's going to be the right way. That's R. Okay, what about this guy? We have a methyl group and we have a methyl group. A methyl group on a carbon and then a methyl group on a carbon. That's not good. That's going to be achiral. And then a methyl group right here and then a methyl group right there. That's going to be achiral as well. Also notice, if you couldn't see that this has a plane of symmetry, right? And so automatically it's going to be achiral, right? And what about this guy? Well, do I have any stereocenters? Well, not really, because a double bonded carbon is never a stereocenter. Never. This could be a double bonded nitrogen. I don't care. It has 2 of the same things attached to it. That's not a stereocenter. This one just has a hydrogen. This one has a hydrogen right there, and then a hydrogen right there. Same deal for this guy. Not good. And so if you fill in the blanks all over the molecule, it's going to be all the same molecule, right? Or all the same atoms. And that means that you don't have a chiral center. You actually have an achiral molecule. So be on the lookout for that. Just to recap, if you have a atom that is double bonded to a carbon, that can never be a chiral center. Yes, it could be attached to a carbon that is attached to a chiral carbon right there. Like in this case, we had a double bonded oxygen attached to a carbon. However, I didn't say, this is my chiral center. I didn't say that. This guy right here in the middle is my chiral center, and attached to my chiral center is going to be a double bonded oxygen. So that's going to be independent. The double bonded oxygen itself is never chiral. Right? So if you have an exam question like that, the double bonded oxygen itself is not a chiral molecule. It's not going to be chiral. Right? What about this guy right there? Well, this looks pretty good actually, right? So just draw in your implied hydrogens, right? And start labeling some priorities. That's going to be number 1. This is going to be number 2, 3, and 4. So 1, 2, 3. Hydrogen is in the back, so it's going to be R configuration for this guy, R. And what about the bottom one? The bottom one is going to be, let's see. Well, I'd rather have an oxygen, right, compared to a methyl group. So this is going to be number 1 right there, number 1. This is going to be number 2, right? I would say number 2. Hold on. Sorry, number 2, so it's more obvious for you, right? The reason why I didn't say number 2 for this guy is because it's too far away from me. It's too far away. So usually I confine myself to this group and this group. I'm not going to be like, oh, you know, oxygen's number 1, let's look over here. That's too far, you know. We have to climb we have to walk through the train compartments first, right? I just can't, you know, jump compartment to compartment. I have to go through each one individually, right? And so yeah, this oxygen is going to be number 1. This CH2 is going to be number 2. Methyl group is going to be number 3. The hydrogen, which is in the back, is going to be number 4. So we have 1, 2, 3, right? Hydrogen is in the back. Therefore, we are pretty happy. We are pretty happy, and that is going to be an S conformation. So that is the wrong way a clock moves. The clock doesn't move that way, right? The clock moves this way. Since we're moving this way, it's going to be S, because that clock is pretty silly. Very, very silly. So for this molecule, we have an R and an S configuration. Alright, before you get started on doing these problems, it's important for you to know that these are pairs, okay? So this guy is connected to that guy. And so really you just have like 10 questions on this page, right? And I want you to tell me if it's going to be the same, if they're going to be enantiomers, or are they going to be diastereomers. And if you don't know, that's okay. You can just watch me do these. And I hope that you learned something, right? Keep in mind that this is like the final stretch. After this page, we have one more. And you'll be done. So let's get to it. Alright, if you're not sure if this is an enantiomer or the same, or if it's a diastereomer, then, you know, you can always just assign priority, which is what you know how to do now, because we've been doing like, I don't know, 50 problems, right? So chlorine is going to be priority number 1. I'd rather have a CH2, that's going to be 2, and you can't really see that. My apologies, that's going to be 1 and 2, 3 and 4. Okay, so what is that? Well, it's going 1, 2, 3. Okay, that's the correct way a clock moves, so that's going to be R. Let's do it over here. We have a chlorine, that's 1, 2, 3, and 4. So that's going to be 1, 2, 3, and 4. Okay. Well, that's a silly way a clock moves. Clocks, they don't move like that, do they? Well, I mean, mine does, but not yours, and you're probably right. You know more than I do. So it's going to be S. That's very silly. And hey, we have an R and an S. What does that mean? Well, if you have, write this down, pay attention. If you have 2 chiral molecules, and one is R and the other is S, or if it is S and the other is R, then they are going to be enantiomers, okay? And I'm going to say that this is enant, alright, because I'm lazy. I don't want to write it out. But because this has an R center and this other one has an S center, and they're both chiral, they're going to be enantiomers. And so they are not the same. They're going to be enantiomers. Right? Let's do another one. This is number 1, 2, 3, and 4. That's going to be an R configuration, same as above. Then we have a chlorine in the back, 2, 3, and 4. Let's see, 1, 2, 3. Oh, that's an R, but the hydrogen is in the front, So I'm going to have to reverse what I did. That's simple. Just put your arrowhead right there. And that's going from 6 to 12 in the wrong direction. That's very silly, right? It's going to be very silly of you to do that. So that's going to be an S configuration. So over here, it's going to be R and S. Turns out that it's an enantiomer. Enantiomer. Enant. Right? Let's go over here in this nice pink color. This is going to be priority number 1, 2, 3, and 4. Over here, we have priority number 1, 2, 3, and 4. Also, this is going to be what? For this left one, it is going from 1 to 3. And that's the correct way a clock moves, so that's going to be R for sure. That's going to be R. And over here, we have 1, 2, 3. That's going to be S, but notice that my hydrogen is in the front. So my hydrogen is in the front. What does that mean? I have to put my arrowhead from here, I have to put it over here. Okay? And that's the correct way a clock moves. So that's going to be R. Now notice that these molecules were both chiral. And notice that I have R and R. That means that they are going to be the same thing. They are the same. If I had S, that's going to be the same. If I had R, S, that's going to be an enantiomer. If I have S, R, that's going to be an enantiomer. That only applies if the two molecules are themselves chiral, right? If I have both of them achiral, then, that doesn't apply. And it gets a little bit more involved if you have two things that are achiral, which we'll see later on. All right. So what about this guy? Well, notice that I have an alcohol group that is on a wedge, and on the other side I have an alcohol group that's on the wedge. And notice that there is actually a plane of symmetry. There's a plane of symmetry, and over here we have a dash dash. That means that there's a plane of symmetry as well. So what does that mean for us? Because if you don't know, you probably forgot, but I'll go over it again. If you have a plane of symmetry, then a possible chiral molecule automatically becomes achiral. So a plane of symmetry that converts a chiral molecule to an achiral molecule, that's called a meso compound. And so for these two guys, if I didn't have a plane of symmetry, yeah, I would be chiral. But because I have a plane of symmetry, that's going to be called a meso. I'm going to call that meso. And that's a meso as well. And so what do we have here? Well, I'm going to say something and you're going to write it down. So let's see. The mirror of a meso, right, is the same. A mirror of a meso compound is the same. So you would agree, right, that this wedge converted to a dash, right? And this other wedge converted to a dash. And so since everything converted, since a wedge became a dash and the other wedge became a dash, we're going to have a mirror. And because these are meso compounds, the mirror of a meso compound is the same. It's going to be the same. So this is not valid, so it's going to be same. Okay. What about this guy right here? Okay. Well, for sure, there's going to be a plane of symmetry right there because we have a wedge and a wedge. On the other side, do we have a plane of symmetry? Well, no, we don't. We don't have a plane of symmetry because that's a wedge and that's a dash, right? Or hash. And so what does that give us? Because, we're not doing so well. But here's the thing right there. Here it is. If you have something let me phrase it better. If one thing changed and the other things stayed the same, it's typically a diastereomer, right? That's a cis-trans relationship. So for here, we have a wedge and we also have another wedge. So that did not change, right? That didn't change. Well, over here we have a wedge, and then over there we have a dash. And that changed. It's the only thing that changed. And so technically, they're going to be diastereomer. Dia. Right? Diastereomers, well, you know, if some things flip in a mirror, then it's going to be a diastereomer. So you would agree with me, right, that we have an alcohol right here, and we have an alcohol right here. We have an alcohol over there, and we have an alcohol over there, right? So it's a mirror. But one of the things in the mirror, specifically this wedge, became a hash. It became different. And that's only one thing, and so it became a diastereomer. So that's a diastereomer. Okay, well, what about this guy right here? What about this guy? Okay, well, we have a hash, and it became a wedge. Then we had a hash, and that became a wedge. And then we had a wedge, and it became a hash. So what's going on here? I don't understand. Well, here's the thing. Here's the thing. Do we have a plane of symmetry? You know, I would say that we don't have a plane of symmetry. I would say that we don't have a plane of symmetry. Okay, so what does that give me? Well, if it doesn't have a plane of symmetry, then most likely it's going to be chiral, right? It's important for you to know. It's important for you to know that the mirror of chiral is enant. And so, you know, technically this is going to be a mirror. We had an alcohol in the same positions, just the same things, they changed, right? So yeah, we have an alcohol right there and an alcohol on each other side, but the only thing is that they flipped, right? So a dash became a wedge, etc. So these are technically mirrors right here, and the mirror of a chiral center is going to be an enantiomer. It's going to be an enantiomer right here. So this is an enantiomer. All right. If you can't see this right here, you know, you can assign priority groups, which is kind of a hassle to do. But if you want to do it, you can. But let's do the shortcut, right? So we have a hydrogen that became a wedge. So this dash became a wedge. This wedge became a dash. Okay, so that flipped. This hash became a wedge, and this dash became a wedge. So that flipped too. Okay, so they all flipped. So they all flipped. And do you see a plane of symmetry? Well, no, because if you were to rotate this chlorine is going to be in the hashes, right? And this chlorine is going to be in the dashes. So you don't have a plane of symmetry. Similar to this guy. This hydrogen, which is on a wedge, would be a dash if you were to rotate it. So if you were to do this, you would have a hydrogen and a chlorine, and then you would have a chlorine and a hydrogen. And so for sure, a chlorine that's on on hashes is completely different from a chlorine that's on wedges, and so they don't have a plane of symmetry. Okay, so if they don't have a plane of symmetry, then most likely it's going to be chiral. And hey, everything flipped in this chiral molecule. So what do you know about the mirror of a chiral molecule? Well, yeah, for sure, it's going to be an enantiomer. It's going to be an enantiomer. Right? All right, what about this guy? Well, for sure, this is going to be a meso compound. Why? Well, for the same reason. If we were to flip this guy right here, this chlorine, well, let's just show it, yeah? Let's just show it. So we have a chlorine going outwards, and the hydrogen going inwards. Right here, then we have a chlorine going outwards, and then a hydrogen going inwards. So that's going to be a meso compound because a chlorine on the wedge is going to be the same thing as a chlorine on a wedge. So that is a meso compound. And what do you know about meso compounds? Well, a meso compound is automatically going to be achiral. It's going to be achiral, right? Let's see over here. Yep, this chlorine, which is a wedge, is going to be a hash when you twist it. So a chlorine hash is going to be the same thing as another chlorine hash. And that's also going to be a meso compound, right? And so these things, are going to be mirrors, right? And so what do you know about the mirror of an achiral molecule? Well, the mirror of an achiral molecule is going to be the same. This applies to achiral and this applies to meso compounds, right? So the mirror of a meso compound or an achiral molecule is going to be the same. It's going to be the same. Right? So, yeah. Or, achiral. And I butchered that, but that's cool. Alright, do we have a plane of symmetry over here? A chlorine with a wedge, and then we compare it with the chlorine with a hash. Is that the same? No, I wouldn't say that, right? I wouldn't say that. Over here, we have a hydrogen with another hydrogen, yeah? So if you can't see that, we have this guy. So that's chlorine with hydrogen. That's going to be chlorine right there. Okay. So for sure, this is going to be meso. But what about this guy? Well, this is not good. This is not good. What, I have something that is actually chiral, because you don't see a plane of symmetry, right? Versus something that is achiral. Oh man, what do I do? Gosh. Well, here's the thing. If this ever happens to you on the exam, where you're comparing something that is chiral versus something that is not chiral, right? Maybe look at your substituents. This one is going out towards you, and this one is going inwards. So you have something coming outwards, you have something going inwards. They're going in two completely different directions. So what is that called when something goes in a different direction? That's going to be called trans. Well, this chlorine is going out towards you, and this chlorine is coming out towards you. So we have two things that are going in the same direction. They have to be the same thing. So chlorine is the same thing as chlorine, right? Well, we have two chlorines that are going in the same direction. That's going to be called cis. We have two chlorines going in different directions. That's going to be called trans. When you're comparing a trans versus a cis, or a cis versus a trans, you automatically have a diastereomer. This is going to be a dia right there. All right. For this guy, we have a mirror flip, because a wedge can be folded onto a wedge, right? And this guy right here, if you were to translate it, it would be like this. First of all, this guy's up. This guy is down. Okay, so we have something going upwards, and then we have something going downwards. Oh, I'm sorry. This is not downwards. I'm sorry. This is upwards as well, and that's going to be down. Okay, so we have something else going upwards, and then this is going downwards. Alright, so we have an alcohol going upwards, and then another alcohol going upwards. In simple terms, we have two things on wedges and two things on hashes. And so, we have a meso compound, because you have a plane of symmetry, right? You can fold them on that line of symmetry. And so what do you know about the mirror of a meso compound or an achiral molecule? The mirror of a meso compound / an achiral molecule is going to be the same. They're going to be the same. So these are the same. Cool. Alright, let's see about these guys. We have a chlorine. It's going to be 1. That's 2, 3, and 4. So that's 1, 2, 3. Hydrogen is in the back, so that's the correct way. That's going to be R. We have 1, 2, 3, and 4. That's 1, 2, 3. That's the incorrect way. That's going to be S. So we have an R compared to an S, that's what? Enantiomers. Alright. We have a chlorine, that's 1, 2, 3, and 4. That's 1, 2, 3, 4. That's going to be R. Over here we have 1, 2, 3, and 4. That's 1, 2, 3. But hydrogen is coming out towards you, so you're going to have to reverse it, right? And put the arrowhead over there. And that's the correct way a clock moves. And here we have an RR. So what do you know about RR? Well, RR is going to be the same, right? It's going to be the same thing. For this one, do we have a meso compound? Well, no, we don't have a meso compound because we don't have two wedges. We have a wedge and a dash, okay? So let's see. We have a wedge, and that became a dash. We have a dash, and that became a wedge. And so we do have a mirror, right? We have a mirror. And, you know, I skipped this guy. I'll come back to it. Okay, so we have a mirror. And, you know, we don't have a plane of symmetry. We don't have a plane of symmetry. So what do you know about the mirror of a chiral molecule? The mirror of a chiral molecule is going to be an enantiomer. So mirror chiral equals enant. Alright. Let's do this guy in green. Okay. Let's do 1, 2, 3, and 4. Okay, so that's 1, 2, 3. That's going to be R configuration. Let's do it over here. 1, 2, 3, and 4. That's still R configuration. So we have RR. That's going to be the same. Alright. Let's see over here. Do we have a plane of symmetry? No, typically, whenever you see a cyclohexane or cyclopropane, whatever, cyclomolecule, you know, just look for a plane of symmetry first. If you can't find it, continue, right? So I didn't find a plane of symmetry because we are comparing a wedge and a hash. So that's not good. But what about this guy? Well, man, that's pretty hard. But whenever you have that happen to you, try to orientate it so that it looks the same. Okay, try to make this the same as this guy. So really, you can just redraw it as follows, right? So we have this guy and that guy. So all I did was I technically twisted the cyclohexane to the right side, right? I just redrew it. I didn't change anything. I just redrew it. So try to match the direction of this guy so that the problem becomes easier. All right. So we're gonna ignore this guy. We're gonna say that this became a hash, and this hash became a wedge. So everything flipped, and we do not have a plane of symmetry. There is no plane of symmetry. And we flipped everything, so it's a mirror. So what do you know about the mirror of a chiral molecule? The mirror of a chiral molecule is going to be an enantiomer. Enantiomer. Okay. What about him? Well, this wedge became a hash, and this hash became a wedge, and this wedge became a hash. Okay, so that's a mirror for real. But notice something. Before you even start working on the problem, you should notice that you have an achiral molecule. How do I know that it's achiral? Well, you can actually do a plane of symmetry on this part of the cyclohexane. So that's a plane of symmetry. That's a plane of symmetry as well. But we said that these are mirrors. So what do you know about the mirror of a meso compound? And what do you know about the mirror of an achiral molecule? The mirror of both of them is going to be what? The same. They're going to be the same thing. So the mirror of an achiral molecule is going to be the same. So this is the same. Okay. All right. Over here we have a hydrogen on the hash. It becomes a wedge. This hash becomes a hash. Oh man, so we only flipped one thing, right? We only flipped one thing. And so for sure, you know, this is going to be chiral, right? Because if you were to do it like this, you would have a chlorine right there and a hydrogen, right? That's a hydrogen and that's a chlorine. Whenever we twist something, whatever was a hash becomes a wedge, and whatever was a wedge becomes a hash. So for sure this is not achiral, because you do not have a plane of symmetry, therefore you have to be chiral, most likely. So we said that both of them are going to be chiral, right? Actually, no. Look at this. Look at this. Okay, so that still becomes an H. It's going to be Cl. This is going to be an H. And this is going to be a Cl. Okay, so this is going to be back, and that's going to be cis. And notice this is going to be front, back for the chlorines. That's going to be trans. And so you're comparing two chiral molecules that has a trans and cis relationship, or cis and trans relationship. What do you know about cis and trans? They have to be diastereomers. This is diastereomer. Alright. This one looks okay with the orientation. This one looks kind of weird, so I'm going to reorientate it. Cl, hydrogen, whatever was a wedge becomes a hash. Whatever was a hash becomes a wedge. Alright, so you have a cis, and then you have a cis. Alright, so cis, what is that? Well, I don't know yet. Well, hold on. This looks like a meso compound because we have a plane of symmetry. If we have a plane of symmetry, that's going to be achiral. And this is also achiral. And they, you know, they look like mirrors as well. And what do you know about the mirror of an achiral molecule? Well, they have to be the same. They have to be the same. Over here, if you can't tell what this is, draw it out. This is up, and this is going to be down. Right, and this guy is that guy. So we have something going upwards, that's going to be a hash, or a wedge, sorry, a wedge. It's going to be OH. This is going to be hydrogen. This is going to be a wedge. And this is going to be a, sorry, that's a dash. And this is going to be a wedge. That's a hydrogen. Okay, so now you're comparing a wedge alcohol with a wedge alcohol. And then we have a dash alcohol with a dash alcohol. Okay, do we have a plane of symmetry? Well, you know, I would say that we don't. Do we have a plane of symmetry? You know, that's a tough one. Well, you know, sometimes it doesn't go that deep into symmetry. Sometimes it just looks obvious. Like, we have a wedge alcohol right here and a wedge alcohol right there. We have a dash alcohol right here and a dash alcohol right there. Well, they are technically the same thing. Yeah, they don't have symmetry, but it's the same thing. Literally, it's going to be the same thing. Before I stop the video, I just want to show one more thing. Right, I just made this one up on the fly. Let's actually show the stereocenters right here. So, would I rather have a fluorine, iodine, or bromine on my first stereocenter? Well, for sure I want an iodine right here. This is going to be a bromine, that's going to be 2, 3, and 4. So that's 1, 2, 3 right here. Right? Okay. But notice something. That my methyl group, my CH, is going to be the lowest priority, right? So I'm going to exchange it with the iodine. I know, it's kind of messy, but so I want to show you. So we have a methyl group right there, and an iodine. So I'm gonna have to erase everything that I did, which sucks, but it's fine. To be honest, I wasn't anticipating me doing that, but I just want to get it over with so I could tell you. We have a priority group number 1, 2, 3, and 4. That's the fourth one has to be in the back, right? So notice that my lowest priority group was not hydrogen, it was actually a carbon, not a methyl group, sorry. It's just a carbon group. So it's going to be 1, 2, 3. Okay, 1, 2, 3. So that's going to be what? That's going to be an S configuration, but we had to move something in the back, so it's actually going to be the reverse. That's going to be clockwise, so it's going to be R configuration. R configuration. Now let's move on to the other guy right here. Let's see, selenium, which is number 34, if I remember correctly. We have a nitrogen, a chlorine, which is number 30. No, chlorine I think was 17. And then we have a methyl group, or a CH group. Ignore this iodine, okay? So let's see. This is going to be priority number 1, 2, 3, and 4. So we're going to have to kind of rewrite it. We're going to have to rewrite it. We have nitrogen right here, and then CH2 group right there. So it's going to be 1, 2, 3, and 4. So it's going to go 1, 2, 3. But we had to change something to the back, so we're going to have to reverse that. So it goes from the clockwise position, so it's going to be R, right? So we had 2 stereocenters. We have 2 stereocenters, right? Okay, so how many possibilities can I have for this stereocenter? Well, that's easy. All you have to do is just put 2 to the n, where n is the amount of stereocenters. So n equals amount of stereocenters. In this case, we have 2 stereocenters. I gave them asterisks, so it's going to be 2 raised to the 2, which is equal to 4 different combinations. So we have 4 different combinations to do. In that case, we can do R, we can do RS, we can do SR, and then we can do SS. So those are my 4 different combinations for stereochemistry, right? And that's all you really have to do. You just have to make sure that your lowest priority group is in the back, always. If it's not, then you're going to have to exchange it with something that is in the back, right? 2 raised to the n is the formula or the equation you need to do to calculate how many stereocenter possibilities you have, right? And so congratulations, you just did around 70 practice problems for stereocenters. I recommend that you do more practice problems because you're going to become a master at them, and eventually you're going to get really sick of them. And so I hope that this video helped you. I hope that you find these videos helpful, and I really hope that you do well on your next exam. I believe in you. I believe that you can do amazing if you put your mind to it. As always, thank you for watching, and thank you for trusting me with your education. Alright, have a great day.